Hello, my name is Ashish Arora and I work as a senior scientist at the Molecular and Structural Biology Division of CSIR Central Drug Research Institute, which is at Lucknow. I work in the area of structural biology, specializing in determination of protein structures using NMR spectroscopy. Here I am presenting you paper 8, Medical Physics, and module number 19. We begin with the NMR phenomena. The objectives of my talk are to tell you what does NMR refer to, how did it develop, what is the history of NMR, what is nuclear magnetism, what is the relation between energy and nuclear moment in the magnetic field, what is Larmor frequency, and what is the sensitivity of NMR spectroscopy. So let's begin with the introduction. NMR refers to N for nuclear, M for magnetic, and R for resonance. This spectroscopy is a component of some very important spectroscopic and imaging techniques like MRI and also like solid state NMR spectroscopy. NMR spectroscopy is an exciting technique to study molecules and has extensive applications in solutions and solid state. In solution NMR spectroscopy, narrow line widths of peaks and strong signals are observed because of rapid tumbling of molecules in solution. In solid state NMR spectroscopy, solid crystalline or amorphous samples are introduced into a rotor and sharp peaks are obtained by spinning the rotor at a magic angle of 54.74 degrees. Magnetic resonance imaging is based on the image viability and/or intrinsic tissue contrast, which is determined by the longitudinal and transverse relaxation times. They are called as T1 and T2, and we will learn about them later, of water protons in cells and tissue in an organism. The application of magnetic resonance techniques. Since the understanding and applications of techniques related to magnetic resonance are so vast, it is difficult to describe the power of the methods in a few words. However, an indication is provided in the Nobel lecture of Professor Richard Arne Ernst, who received his Nobel Prize in 1991, and from which I share with you a few inspiring quotations. The first one: the world of the nuclear spins is a true paradise for theoretical and experimental physicists. But not only for physicists is nuclear magnetic resonance of great fascination. More and more chemists, biologists, and medical doctors discover NMR not so much for its conceptual beauty, but for its extraordinary usefulness. Then Professor Richard Ernst has written, I am not aware of any other field of science outside of magnetic resonance that offers so much freedom and opportunities for a creative mind to invent and explore new experimental schemes that can be fruitfully applied in a variety of disciplines. NMR is intellectually attractive because the observed phenomena can be understood based on a sound theory, and almost all conceits can also be tested by easy experiments. So what are the advantages of magnetic resonance techniques? The general advantages of magnetic resonance is, as enunciated in the Ernst Nobel lecture, are: the nuclear sensors provided by nature are extremely well localized with a diameter of a few femtometers and can report on local affairs in their immediate vicinity. It is thus possible to explore molecules and matter in great detail. The interaction energy of the sensors with the environment is extremely small, with less than 0.2 joules per mole, corresponding to the thermal energy at 30 millikelvin. And the monitoring of molecular properties is virtually perturbation free. Nevertheless, the interaction is highly sensitive to the local environment. Geometrical information can be obtained from nuclear pair interactions. Magnetic dipolar interactions provide distance information, while scalar J coupling about which we will learn further. Interactions allow one to determine dihedral bond angle. History of NMR. We'll learn about it in next few slides. The discovery of magnetic resonance is somehow related to the Zeeman effect. Zeeman effect is splitting of the spectral lines of an atom in the presence of a strong magnetic field. Wolfgang Pauli was deriving an explanation for the Zeeman effect in atomic spectroscopy, and he proposed his famous exclusion principle. The Pauli exclusion principle states that no two electrons can have the same values of the four quantum numbers n, the principal quantum number, L, the angular momentum quantum number, m, e, the magnetic quantum number, and m, s, the spin quantum number. However, Pauli had only proposed a fourth quantum number, and it was christened as spin by Uhlenbeck and Gaudsmit in 1925. History of NMR Spectroscopy-II. The Pauli's principle was extended to fermions, which include all quarks and leptons and composite particles such as protons and many other atoms. While the total angular momentum of an electron can be distinguished into orbital angular momentum and spin, the nuclear is taken as a single entity and its total angular momentum is referred to as nuclear spin. Associated with each nuclear spin is a nuclear magnetic moment which produces magnetic interactions with its environment, and the forebearer of the angular momentum quantization in atomic scale system was the classic Stern and Gerlach experiment. In the Stern and Gerlach experiment, a beam of silver ions was passed through an inhomogeneous magnetic field, and the resultant beam was found to split into two components. This original method was further expanded. The molecular beam method was used for studying magnetic moments of various nuclei. The most significant improvement of this era was the introduction of magnetic resonance method by Isidor Rabi. Rabi predicted that the magnetic moments of nuclei could be induced to flip their magnetic orientation if they absorbed energy from an electromagnetic wave of the right frequency. Isidor Rabi extended this work by passing a beam of molecules through a vacuum chamber and subjecting it to radio waves and varying magnetic field strength, thereby introducing magnetic resonance method. Rabi's experiments involved passing a beam of molecules through a vacuum chamber and subjecting it to radio waves and varying magnetic field strength. By adjusting the external magnetic field and the radio frequency, he was able to observe magnetic resonance absorption. Rabi's experiments helped in accurate measurement of magnetic moments. It went to almost a tenth after the decimal place, actually 0.1 value. Bloch extended this work by proposing to detect the reorientation of nuclear moments in bulk phase, which was 1 ml of water, through the methods of radio reception. Till Rabi's experiments, we only had molecular beams discussing with solids, and Bloch brought in the chemistry. He brought in a bulk phase 1 ml of water. The signals to be detected would be due to the electromagnetic induction caused by nuclear reorientation and would appear as a voltage difference between the terminals of an external electric circuit. Next, Bloch developed his theory in terms of surplus of spin in a bulk system or nuclear polarization, which is both parallel and proportional to the applied homogeneous magnetic field. To a stationary sample in homogeneous magnetic field, Bloch applied a perpendicular alternating radio frequency field. This led to an alternating magnetic field which could generate electron motive force in a suitably wound coil. By rectification and application, and amplification, this EMF could be recorded on a voltmeter with the signal in the range of millivolts. Bloch contributed the famous Bloch equation and the theory of relaxation to NMR spectroscopy, about which we will learn further. Simultaneously, Edward Purcell detected the same phenomena in paraffin wax. Purcell's experiment involved the electrodynamical aspect of absorption, which was manifested through the increased loss of a cavity resonator under resonance conditions. In his later experiments, the cavity was replaced by a radio frequency bridge, which contained in one arm a coil surrounding the sample. As a consequence of nuclear induction under resonance conditions, a change of the impedance of this coil occurs, which leads to a readily detectable change in the balance of the bridge. This change in impedance is complex, with its real part corresponding to absorption and its imaginary part to dispersion. Bloch and Purcell both received Nobel Prize in 1952, and their papers were also published in physical reviews almost back to back, and these papers are actually available from the online site of the journal Physical Reviews. Next slide, please. A quantum leap in sensitivity and applications was achieved by Richard Ernst in the form of pulsed Fourier transform NMR spectroscopy. This technique revolutionized high-resolution liquid-state NMR spectroscopy and extended its application to studying molecular complexity, dynamics, exchange phenomena, and imaging. It made possible the multidimensional NMR experiments that allowed measuring of NOEs, coupling constants, relaxation times, and exchange phenomena for small and larger molecular systems. And these developments were simply amazing. They opened the floodgates for application of NMR to various systems and generated very exciting information about which we'll learn further. The application of NMR spectroscopy for three-dimensional structure determination of proteins and nucleic acids at atomic resolution in the solution state was extensively developed by Kurt Wuthrich, who demonstrated the power of NOE-based methods for structure determination. Here I should mention that both Richard Ernst and Kurt Wuthrich have received Nobel Prizes. Richard Ernst in 1991 and Kurt Wuthrich in 2002. Rapid developments in pulse techniques, magnet field strength, probe design, labeling methods, and electronics has made studying the structures, dynamics, and functions of large macromolecular systems amenable by NMR spectroscopy. The highest field strength spectrometer in the world is operational at Lyon's European Nuclear Magnetic Resonance Center in France. It has a 23.5 Tesla magnet corresponding to a proton frequency of 1 gigahertz. Here I must tell you that 1 Tesla is equal to 10 raised to the power 4 Gauss, and for comparison the Earth's magnetic field is 0.5 Gauss. The safety limits for magnetic cards is around 5 Gauss. Modern NMR spectrometers are equipped with cryogenically cooled probes that significantly increase the sensitivity. So here you see the Nobel laureates in the area of nuclear magnetic resonance. You have Isidore Rabi, who got Nobel Prize in Physics in 1944 for his resonance method for recording the magnetic properties of atomic nuclei, which was followed by 1952 Prize in Physics to Felix Bloch and Edward Purcell. Bloch was at Stanford and Purcell at Harvard for their development of new methods for nucleic magnetic precision measurements and discoveries in connection therewith. And then there was a gap, but there were many NMR related Nobel Prizes in between. And finally, in 1991, Richard Ernst was awarded Nobel Prize in Chemistry for his contributions to the development of methodology of high-resolution nuclear magnetic resonance spectroscopy. And in 2002, as I already told you, Kurt Wuthrich received Nobel Prize in Chemistry for his development of nuclear magnetic resonance spectroscopy for determining the three-dimensional structure of biological macromolecules in solution. And the following year, in 2003, Lauterbur and Mansfield were awarded Nobel Prize in Medicine for their discoveries concerning magnetic resonance imaging. Now we come to the nuclear spin angular momentum. The nuclear spin angular momentum is a vector quantity and its magnitude is given by a dot product I dot I and the square root of it. Nuclear spin angular momentum is an intrinsically quantum mechanical property that does not have a classical analog. And this is very important because most of the students would come around a very simplified explanation of rotation of charge, the nuclei being charged, so a rotating charge producing magnetism. But in actuality, nuclear spin angular momentum does not have a classical analog, and it is an intrinsically quantum mechanical property, and its various manifestations are best dealt by applying the quantum statistical methods. The spin angular momentum is characterized by the nuclear spin quantum number I, and there are certain features. For example, nuclei with odd mass numbers have half integral spin quantum numbers. For example, proton 1H, 19F fluorine, 31P phosphorus. Nuclei with I is equal to half, particularly hydrogen, are most important for NMR spectroscopy. Nuclei with an even mass number and an even atomic number have spin quantum number equal to 0. For example, helium, C12, O16 and S32. Nuclei with an even mass number and an odd atomic number have integral spin quantum numbers, like deuterium has I is equal to 1 and 14 has I is equal to 1 and boron 10 has I is equal to 3. Nuclei belonging to the first category are NMR active, the second category are NMR inactive. Nuclei with spin quantum number greater than half also possess electric quadrupole moments arising from non-spherical nuclear charge distributions and consequently have very short relaxation times, which corresponds to broad line widths, and they have limited applications. Nuclear spin angular momentum. Nuclear magnetism and NMR spectroscopy are manifestations of nuclear spin angular momentum. The nuclear spin angular momentum I is quantized, and the different quantum states are characterized by a nuclear spin quantum number I, and it is given as I is equal to h cross, which is h by 2 pi, square root of I bracket I plus 1 bracket closed. In NMR spectroscopy, the Z or Z component of the angular momentum Iz is chosen to be specified simultaneously with the magnitude. So, Iz is equal to h cross dot m, where m is magnetic quantum number and it has values from minus I to I plus 1, which are in total 2I plus 1 possible values. Iz is restricted to integral steps of h cross and magnetic quantum number m ranging from minus I to plus I. For a spin half system, m has two values of plus half and minus half. Nuclei that have non-zero spin angular momentum also possess nuclear magnetic moment, which is given by mu. The nuclear magnetic moment is collinear with the vector representing the nuclear spin angular momentum vector, mu is equal to gamma I. The magnetic moment of a nuclear spin, mu, is proportional to its spin angular momentum by a factor called as the gyromagnetic ratio, gamma, which has units of radian per second per Gauss. Mu z is equal to gamma IC is equal to gamma h cross m. The magnitude of gyrometric ratio depends on the type of nuclei. The magnitude of gamma in part determines the receptivity of a nucleus in NMR spectroscopy. Because angular momentum is a quantized property, so is the nuclear magnetic moment. Now, effect of static magnetic field on nuclear spin precession. In the presence of static magnetic field B, the nuclear spin angular momentum I begins to precess around the axis of the field and traces out a cone-shaped surface as is shown in the figure. The location of angular momentum vector I on the surface of the cone cannot be specified because of quantum mechanical uncertainties in the Ix and Iy components. The up and down cones represent the two different spin states. Energy of the nuclear spin in magnetic field. In the presence of an external magnetic field B, the spin states of the nucleus have energy given by the equation E is equal to minus mu dot B, where B is the magnetic field vector. The minimum energy is obtained when the projection of mu on B is maximized. Because of the quantum mechanical restrictions, mu cannot be collinear with B and the M spin states become quantized. For the geometry of a conventional NMR spectrometer, the static magnetic field B is directed towards the z-axis and is shown as B0 of the laboratory coordinate system. For this geometry, the energy of interaction or Hamiltonian between the static external magnetic field of field strength B0 and the spin state of the nucleus is given by E is equal to minus mu B0. The energy of spin quantum state mz of the nucleus in terms of nuclear magnetic moment and external field strength is given by Em is equal to minus gamma Iz B0 is equal to minus gamma h by 2 pi mz B0. Many times it is assumed that energy is expressed in the units of h cross or h by 2 pi, and therefore h cross is not explicitly written. In the presence of static magnetic field, the projections of the angular momentum of the nuclei onto the z-axis of the laboratory frame Iz results in 2i plus 1 equally spaced energy levels, which are known as the Zeeman levels. The energy is directly proportional to the magnitude of the static magnetic field. For a spin half nuclei, there are two states, mz is equal to plus half and minus half, and the energy states are shown in the figure. The energies of the Zeeman level. For an isolated spin of I is equal to half nuclei, only two nuclear spin states exist, m is equal to plus half and minus half, which define two energy levels that are separated by delta E is equal to h cross gamma B0. These levels are obtained by application of an external magnetic field. A single Zeeman transition between the energy levels exists. The spin state with m plus half is referred to as the alpha state, and the state with m is equal to minus half is referred to as the beta state. If gamma is positive, then the alpha state has lower energy compared to the beta state and vice versa. The value of delta E is very small, as a consequence of which the lifetime of the excited state are of the order of milliseconds to seconds. A long lifetime provides narrow resonance lines. It allows for polarization transfer in multidimensional experiments and for mapping molecular motions over a wide time scale. Resonance between Zeeman level transitions and applied RF field. The transitions between Zeeman levels can be stimulated by applied electromagnetic radiation in the radio frequency range, and that is why it is called as an applied RF field. The selection rule governing magnetic dipole transitions is delta M is equal to plus minus 1. The energy delta E required to excite a transition between M and M plus 1 Zeeman state is delta E is equal to h by 2 pi gamma b0, and by Planck's law delta E is equal to h by 2 pi omega, where omega is the angular frequency of the required electromagnetic radiation. Hence, omega is equal to delta E divided by h cross is equal to gamma b0, or omega is equal to gamma b0. This equation is the famous Larmor equation. In the Larmor equation, omega refers to the absorption or resonance frequency of the nucleus. The Larmor equation shows that the absorption frequency or Larmor frequency of a transition is equal to gamma multiplied by the strength of the magnetic field B0 at the nucleus. The sensitivity of NMR spectroscopy depends upon the population differences between Zeeman states. The population difference is on the order of 1 in 10 raised to the power 5 for proton spins in an 11.5 Tesla magnetic field. And this you see here is the concept that Bloch was referring to. As a result, NMR is an insensitive spectroscopic technique compared to techniques such as visible or ultraviolet spectroscopy. Now, here are the magnetic properties of some of the nuclei. We have proton, deuterium 31p, 23 sodium, 14N, C13, 19F, and N15. What you have to see basically is that these various nuclei have I equal to, which is given as the net spin, half or 1 or 3 by 2, and then their gyrometric ratios are given in the terms of megahertz per Tesla. So, a proton has a gamma in terms of megahertz per Tesla of 42.58, and nitrogen has of minus 4.32. This is nitrogen 15, which has a spin of half. C13 has a spin of half, and its gyrometric ratio is 10.71 megahertz per Tesla. There is also a concern about the natural abundance. The proton nuclei is highly abundant, 99.985% abundant, compared to the deuterium, which has significantly lower natural abundance. Compared to that, the NMR active carbon nuclei C13 has a natural abundance only of 1.108, whereas the N15, which is again a spin half nuclei, has natural abundance of 0.37. So, lower the abundance, more insensitive the detection becomes. Bulk magnetic moment and the bulk angular momentum. So far we have talked about a single spin in magnetic environment, but when we talk about the whole sample, then it has a collection of spin. The bulk magnetic moment M of a macroscopic sample is given by the vector sum of the magnetic moment mu for individual nuclei, and the bulk angular momentum J of a macroscopic sample is given by the vector sum of the spin angular momentum I for individual nuclei. At thermal equilibrium, the transverse components, which are the x or y components of mu and I for different nuclei in the sample, they are uncorrelated and sum to 0. The small population difference between energy levels give rise to a bulk magnetization of the sample parallel to the static magnetic field. M is equal to M0K, in which K is the unit vector in the z direction. Population difference and sensitivity. The bulk magnetization longitudinal to the static magnetic field M0 is given by M0 is equal to N gamma square H cross square B0 I bracket I plus 1 bracket closed divided by 3 kBT, where N is the total number of spins, which actually means sample concentration, Kb is the Boltzmann constant, and T is the temperature. At equilibrium, the different energy states are unequally populated because lower energy orientations of the magnetic dipole vector are more probable. The sensitivity of NMR spectroscopy depends upon the population differences between Zeeman states. Based on the Boltzmann distribution, the population difference between the two spin states is given as follows: Na minus Nb is equal to n h cross omega 0 by 2 kBt. For spins with a Larmor frequency of 500 megahertz, this difference is of the order of 4 into 10 raised to the power 5 n at room temperature. Since omega is equal to gamma b0, the population difference and hence the sensitivity depend on gamma, that is the nucleus type with proton having the highest sensitivity, and also it depends on b0, i.e. that is the field strength. The consequence of having a small population difference is that NMR spectroscopy is a relatively insensitive experimental technique because of the small excess of spins in the ground state. Due to the low sensitivity, NMR spectroscopy requires higher sample concentrations, usually of the order of 0.1 to 2 millimolar. Further, the signal to noise of the spectrum has to be improved by signal averaging. So, with this we come to the end of this presentation, and I like to summarize whatever we have learnt here. NMR spectroscopy is a manifestation of nuclear magnetic moments. Nuclei have an intrinsic quantum mechanical property which is called as nuclear angular momentum or nuclear spin. Nuclear angular momentum has a corresponding collinear magnetic moment. The ratio of magnetic moment to angular momentum is a constant for a given nuclei and is called as the gyromagnetic ratio. Gyromagnetic ratio determines the sensitivity of nuclei in NMR spectroscopy. Of particular interest are nuclei with spin I is equal to half. In the presence of a static homogeneous magnetic field, the nuclear spin states have two energy levels, alpha and beta, with a single Zeeman transition. There is a small population difference between these two levels, and a transition can be brought about by electromagnetic radiation in the radio frequency range with frequency that is equal to the Larmor frequency of the spin omega is equal to gamma b0. The sensitivity of NMR technique is low because of small population difference between the states, and the signal to noise can be enhanced by using high sample concentration, multiple signal averaging, and by raising the magnetic field strength. Thank you.